If you have an interest in the functional roles of neural oscillations, you've almost assuredly come across some phase-dependent effects. So for example, you might be interested in the motor mu rhythm and whether the phase of this oscillation alters cortical excitability. So do motor evoked potentials change their amplitude across the mu phase cycle? Alternatively, you might apply transcranial alternating current stimulation, or TACS, over visual cortex and assess whether the phase of the injected alpha rhythm modulates visual target detection thresholds. In both of these cases, we're wishing to model some outcome variable with respect to the phase of the underlying oscillation, whether this be some endogenous oscillation in the EEG or an exogenously applied one in the case of TACS. And as the researcher, we need to make a decision about how best to deal with phase. Should we attempt to target perhaps the defined peaks and troughs of our oscillation? Maybe we expect our effect to be the largest there. Or should we forego any worries about exact stimulus timing and just let phase be a random factor? So in silico, or in simulation, we have an opportunity to quantify the statistical power of those scenarios because we have control over the truth of whether a phase-dependent effect exists or not. So I aim to demonstrate to you that under most experimental scenarios, phase binning, where trial averages are taken across a defined kind of phase range, is suboptimal. So when particular points of the phase cycle are perfectly targeted with no error, it's a very reasonable thing to do to take the averages of these across the different phases. So for example, you might do a t-test between the 0 and 180 degree phase bins, where you might expect this effect to be the largest. But in reality, phase targeting is burdensome on the researcher. You have to target your stimuli relative to the waveform, and this is often not trivial, especially when your oscillation is coming from the EEG. It's inherently imperfect and kind of unpredictable. So in order to know what state the oscillation will be in the near future, you need to project that oscillation forward in time, and this is of course prone to error. It's not perfect. So here's an example of a really nice study from the Siebner lab. Christopher Madsen and colleagues were targeting the motor mu rhythm with TMS, and this was the observed spread of errors. So on average, the forward prediction does a great job. You can see that those delivered phases are clustered around those cardinal phase bins, but there's a lot of error even when everything is done right. So 45 degrees is the half width of these phase bins, and with a 50-degree absolute error, it's quite substantial. Another subtler point is that you are assuming that all participants have the same preferred phase. And what I mean by that is that we assume each individual will respond maximally at the same point in that phase cycle. So there are cases where this is probably a safe assumption. So if you're applying TACS over motor cortex, you're going to have a current that's oscillating between anodal and cathodal kind of phases. And so we have strong predictions about how that's going to impact cortical excitability. But there are many cases where it isn't a safe assumption. So for example, if you're looking at alpha oscillations in visual cortex, the phase at which participants perform the best in terms of maybe visual detection thresholds can actually be different because of conduction delays in visual cortex. So something that many researchers will do is just let phase be a random variable. The bin averages are formed kind of post hoc by backsorting the trials. So this is obviously easier for the researcher. It's kind of thoughtless in a way. You just let phase be a random variable. But as you can see in this image, by failing to sample all the data at the extrema, say at the exact peaks and the exact troughs, our bin averages will necessarily regress toward the mean. So there was a very nice registered report published last year from the Hanselmeyer lab, and they had a look at episodic memory encoding relative to the phase of 4 Hz TACS, but they didn't find an effect despite a pretty well-powered experiment. 120 participants did 2 sessions each. And so there's a lingering question of could they have done a better job in terms of quantifying that phase dependency rather than backsorting the trials post hoc. And just to restate this point, because I will touch it on the next slide, any test across participants would again be assuming that they have the same preferred phase, even if those trials are being backsorted into phase bins. So if participants differ on their preferred phases, so here's a toy example where 3 kind of idealized response curves differ by their preferred phase. What researchers will do to try and pull participants together is align them based on the kind of maximum value. So this procedure by definition selects for extremeness, even under the null hypothesis, by choosing everyone's greatest data point or greatest preferred phase bin or whatever you want to call it. We're systematically going to inflate the effect at that phase point. So in order to correct for this, we actually need to remove those trials from the alignment from the further analysis. So this is going to be a loss of power because of a loss of trials. So what we ideally need is an approach that allows phase to be sampled without phase bins, allows preferred phase to vary across participants, and therefore we can preserve all of our trials because we don't need to correct for that bias. So circular to linear regression achieves this, since we're analysing the per-trial data and we treat phase as a random variable where the amplitude, the phase, and the bias are all free to vary. We're essentially just fitting an ideal sinusoidal model to our outcome measure, which minimises the squared cost, as we do in regression. And we can test these models for significance by shuffling the data pairs to disrupt any phase dependency, and we can just fit those amplitudes or those ideal models to the shuffled data and form a surrogate distribution under the null. And we can then compare our observed kind of fitted model to that kind of bootstrapped distribution under the null hypothesis. So if we pair the regression technique with this permutation approach, we actually know that this is one of the best ways of detecting usually quite weak effects of kind of sinusoidality or phase dependency. And this is true across a range of experimental scenarios, whether it be the number of trials, the number of phase bins, the effect size. Generally, it's just one of the better approaches. But because regression can be applied to both raw trial-by-trial data and to the averages that are formed once we backsort the trials, say post hoc, we can directly quantify the cost of this backsorting procedure. So I've got some metaparameters here, and I'm going to backsort the data into 4, 6, or 8 phase bins. And I'm going to contrast these scenarios to the case where we perform the regression on the per-trial data with no backsorting. So what you can hopefully see here is that all the approaches start with the same false discovery rate. They're all, finding 5% of significant experiments when there's no effect. But when there's a small effect, which I've chosen kind of arbitrarily to be around 20% power, or a large effect, which I've chosen to be around 80% power, the bin-free approach has the greatest proportion of significant experiments. So it's got the best statistical power, best sensitivity. And actually, generally speaking, the fewer phase bins there are, the less sensitive the regression is. And the reason for that is that we're, by definition, averaging over a wider phase bin. By having kind of those larger phase bins, there's fewer of them. So what we're seeing in this graph is purely a cost of backsorting. We're using the same regression technique for the kind of phase continuous, bin-free analysis, but also with the backsorting analyses. But there's still a preference in the kind of literature for more traditional analyses like t-tests. So I want to also contrast the regression approach to those, for example, unbiased t-test approaches that you'll sometimes see. So I've got the same metaparameters that I've run before. I'm going to now run t-tests between the bins adjacent to that used for the alignment procedure, so on either side. And I'm going to compare those to the phase bin that's opposite, kind of exactly 180 degrees away. And I'm going to contrast those to the regression approach with no backsorting. So over and above backsorting, regression with permutation is much better than performing t-tests. So the differences here are quite massive. And the main reason for this is that the t-tests are only being performed on a subset of the trials. So I've left the original bin-free regression approach there just as a point of comparison. And it's worth emphasizing that these approaches are analyzing the exact same data with the exact same effect sizes, just in 2 different ways. The regression approach is including all the trials, and the t-tests are performed just on the subset. I think it's also worth emphasizing the effects of tax are likely to be quite small, so they're likely to have small effect sizes. And so we need to give ourselves the best chance of detecting these phasic effects. And so this is where we have the most to gain by using more powerful statistical approaches like regression. So with that, I've hopefully convinced you that you should think seriously about regressing phase as a random factor rather than using phase bins, or to perhaps even revisit old data that might benefit from this more powerful approach.